resistor with R1 and R2. This was the here. So let's see what we are doing here. And a collector resistance or none, it doesn't matter. So this is going to generate a IC, constant. A constant current of IC, simply by creating a voltage at that point, VB. This is base voltage. Then we know that the transistors drop 0.7 volt whenever current flows. So this voltage will be equal to VB minus VBE. And if you put a resistance in here, RE, then IE will be equal to VB minus VBE over RE. And IE will be a constant voltage generated in the emitter path, which will approximately equal to the IC. So we can generate a constant current here in the collector path. In other words, if I short, there will be no change in the current there, because the current is dictated from here. So this is how it was established. It was the emitter current that established the collector current. So if I short that, currents stay constant. If I take it to a positive, more positive voltage, it should stay constant. If I bring it a little down by putting a resistor, drop a little, provided I don't saturate the transistor, still it is a constant, you see? So this is actually a constant current source, that collector path. Between here and here, between these 2 points, X and X, between X and an X, you have a constant current. You have I constant equal to VB minus VBE over R. Okay, so apparently this is a very good approach, and it is indeed a very good approach to generate a constant current. But there's one property with the constant current when it comes to the application. There is a dynamic resistance between collector and an emitter, RO, which is coming from the VA. So here RO is VA plus VCE quiescent divided by IC. That resistance which exists there. That resistance, in the case of the constant current, is going to show itself here, internally, which will render the current source that you built as less ideal, like the one that I drew over here. So this is the ideal. This is coming from the VA, that it is not really completely a constant. When you change the voltage in the collector path, the VCE, there will be a tiny, tiny amount of the change in the collector current, because the current going through that resistor by creating a voltage between X and X, the total current is the sum of the two. So if you put a voltage between X and X, that means you change the voltage of the collector, you're going to see different total current flowing between X and X because of that resistance. There is one method of creating this current, especially being able to create a mirror image, like a copy that current into another branch. So that's great. This is a great current source, but what is not, I don't have a copy of that one. I would like to have this resistor, and also in the meantime I have other branches that duplicating that current. It's going to be useful in the semiconductor design. So the popular source for that one is this one here. If you put a positive voltage, R, they call them usually RRef, reference, and you connect that to a transistor like that, Q1, and this is IC1. and you take it to another transistor, identical transistor, and you take it to somewhere, IC2. If we assume transistors are ideal transistors, then you will have a current here, IB2, a current here, IB1, a current in this path, the sum of the two, IB1 plus IB2. And then if you establish a current in the reference resistor as Iref, I reference in that resistor, then with the help of the equation that is established there, down there, we can validate. Iref is equal to IC1 plus IB1 plus IB2. Here. Iref is IC1 plus IB1 plus IB2. That's equation number 1. But VBE1, if you notice, is identical to the VBE2. These two voltages are the same because that's the same node. Emitter, grounded are the same node. So VBE of that is exactly identical to the VBE of this one. Therefore, IC2 must be exactly a copy of IC1. This must be equal to IC1 because remember the formula for the transistor. IC is IS, saturation current, e to the power VBE over VT. If the two transistors are identical, their VBEs are identical, and their ISs are identical, and their temperatures are identical, VT. VT, remember, it was a room temperature dependent, KT over Q. But if these two transistors are fabricated on a chip, an IC, which is like a few micrometer, 10 micrometer by 10 micrometer in dimension, they're practically right next to each other, terminally. So they will copy each other's temperature, identical temperature. Therefore, VT will be identical. So, if their physical size is identical, their concentration of carrier flow, which determines the betas are identical, and the base emitter voltages are identical, the way that we set up here, then the two ICs will be copy of each other, completely identical. So it makes IC2 equal to the IC1. Now, the fact that IC1 is equal to that, and IB2 is equal to IC2 over beta, doesn't matter which beta, then IB1 will be also equal to IC2 over beta, IC1 or IC2 over beta. So if you substitute all of them back into the first equation, you will end up with IC2 being equal to, here, IC2, which is the current of that transistor, being equal to beta over 2 plus beta of Iref. Iref is the current that is established in that resistor, some reference current. Can be easily established. How? Here. Whatever voltage is there, 10, 15 volt, this is 0, that's a 0.7. So this is 0.7. So what is remaining on the RF is supply voltage minus 0.7 divided by RF. So you establish a calculated current for the Iref. There it is. Iref is equal to VCC minus of VBE1 divided by R, or RF. So this sets the current. Sets the current. So we can create a current in this path, which is copy of the current that is coming in this side. That is like a mirror image, assuming IC2 is equal to IREF, assuming beta over 2 plus beta is almost equal to 1, because beta is usually a large number. Now the nice thing about this arrangement, gentlemen, is we can copy. Put transistors here, third one, fourth one, fifth one, connect all the bases to one place, and all the rest will generate their own currents in that. So they can simultaneously bias other stages from one common source, coming from one common source. And that is significant, that is significant. So this is a popular type, mirror imaging is a popular type, yes?
Where does the, like, for IC2 come from? Like the dots are going on.
Is it this one?
I mean, like on the, like the figure you're showing there. Like
Here?
Yeah, like what is part of
Oh, this?
Yeah,
Yeah, come here, show me.
this.
Oh, this could be anything. It could be going to transistors, like it will go there. You know, the differential pair, etc., or anything else. You see? This will be feeding the emitter current of both transistors. That's where I'm leading to. You know, in a minute we will get there. So it is sending a constant current supplying to both. And if you connect both grounds, put the base to the ground, again, VBE of this identical to VBE of that. So what you will have, this current, half of it will go into here, 1/2 of IREF, the other 1/2 will go into here. See, it's coming forward. I mean, let's take a little time, we'll get there. But it can go anywhere. It can go to a resistor, wherever you like. It's a constant current. As long as you haven't saturated that stage. You know what that means? This VCE2 is greater than 0.7. You've got to make. If this sinks below, like nearly 0.1 of a volt, you're not going to get current here. If this goes 0.1, and this is a 0, already this transistor goes into its passive region. You know, it becomes, it's not active anymore. So that beta IC relation will not work. So this voltage has to be higher than the base emitter voltage for that relationship to work. IB2, IC2, beta times relationship work. They don't work if they go to saturation. This guy never goes to saturation because you see, VCE of that is equal to the VBE of itself, so VCB is 0. Even if VCB is 0, remember transistor is active, still active. It is when collector to base becomes like a negative. That means this voltage goes below that voltage. So we get this one. It's a legitimate current source. And the nice thing about that is you can take that current here from here and bias a PNP transistor exactly the same way. See, you need a reference in here, IREF approximately. Because that branch, as I said, is equal to the current over there. So we can create that current in this branch. And that PNP transistor, which is wired exactly by the same philosophy as the lower one, will create IREF in here. IREF in that path, which is now going to serve in professional operation amplifiers. It will serve the collector resistance going elsewhere. This will become the RC, like the collector resistance of another common emitter amplifier, which means it will supply the current from here, and its dynamic resistance will be not RC of 1 kilo ohm, 2 kilo ohm. It will be RO of that transistor, which could be 100 kilo ohm. So remember we, in the common emitter amplifier, we used to have a gain of 100, because the RC was 1K, 2K, 3K. What about if your RC is 100K? 50 times more. Well, then your gain of 100 or 180 will be 50 times 100 or 180. It will be 10,000 out of one common emitter amplifier. So this is known as active collector with a large dynamic resistance. It will be able to bias it. One disadvantage that exists with this current source is what is, in practical situation, RD. Output resistance. Okay, if we draw the small signal equivalent circuit of that, you will see the diagram below. The diagram is drawn below. Do you all have this handout or not? I saw some people just came in. You don't have it? You don't have it? Because without that, it just doesn't mean anything. We're talking about it. You don't have to write it, just listen. So, oh, sorry. You too? Yeah, because I see many people didn't collect. Still there.
It's from last week.
From last week, yeah.
Oh, yeah.
You have it? Okay. So, in order to check and see what will be the dynamic resistance here, after we know all about the DC conditions, how do we know? Well, I just calculated here. Gave you a formula with values and data. You can predict what is the current here. That would be your IC. And then you need to know the VA of this transistor, the early voltage of the transistor, and then there you are. VA plus VCE quiescent of that transistor divided by IC. VCE quiescent can be said to be voltage from here to here, which easily can be calculated. And it is not that significant because usually VCE quiescents are much smaller than VA here. So if you delete that, you notice that the RO is dependent on the early voltage and the choice of the collector current. So the lower you bias, the higher or more ideal current source you can get out of the transistor. Now, the dynamic resistance. So what is the dynamic resistance? If I make a change in here in the collector emitter, how much change will be there in the collector current? The one that you think is permanently fixed to IREF. So it's not ideal. So model at the bottom shows it. Small signal model of that, small signal model of this, draw them, and you will end up having here our ref, and then this will be the C1, and that will be the RO, or output resistance of the transistor number 1, the current source over there, then going to the ground, and this is a wire, which is that wire here, coming to the base, going straight to the R pi, VBE1 of the transistor number 1, the plus and the minus, and this will be GM times VBE1, GM times VBE1, and current in this line, And given this, then you will go to next one, R pi of second transistor, emitter of the second transistor, this is E1, going to that source, which is GM multiplied by VBE of 2, this is the VBE of 2, and then going to the RO, and this is the collector of transistor 2, emitter of transistor 2, and this is what we are looking at. If you call this X, this is where we are looking at, X. So if you look inside towards that, and you look for output resistance, what will you see? Refer to that diagram, you will see what the answer is. Base doesn't, any change that is here can reflect on the other side, although minutely, but nothing can happen here because signal flows from base towards the collector in a transistor, not from collector towards the base. Have you ever seen changing IC, hoping to get a voltage at the VBE? Well, we changed emitter getting signal at the collector, like common base. We got collector grounded, fed a signal at the base, we got out of the emitter. But we never gave a signal at the collector trying to pick up the output from the base, you see? So there's an opening in here. Put the test voltage here, this will not respond because it needs a voltage in here, and there's no way of creating voltage here. So test voltage here, we'll see this open. We test, and then therefore I of the test will be V of the test divided by RO. Bottom line, the output resistance is this now, RO. The collector to emitter resistance of this last transistor, which is quite high, about 70K, typically 50 to 70, 80K, but it can be way, way better. This is called the second type of the current source. Again, it's a mirror, like that one. Equations are a little bit more involved because we have emitter resistance, but let's check it. So analysis is done in here. Here, just erase it. So you've got to actually learn what I'm lecturing in here in order to appreciate what the differential amplifier is going to do for you see, when we incorporate that type of the current source. So here is the second method. Very similar to the first one. Actually, there is an example of it here. RREF, something to establish the current. RE, an emitter resistance is incorporated here, which goes to a second one. Again, RE, identical emitter resistance, and then the ground. VCC, this is IC2, feeding circuits above, whatever it is feeding. And then we get C2, E2, D of the 2, D of the 1, E of the 1, This is the C of Q1 transistor, Q1 and Q2. Okay. Here are the currents that we are setting up. Here is IREF, reference current that we can easily establish. And then we have IC1. We have a current in here, which is the sum of IB1 plus IB2. This is IB1, and that is IB2. And here is a current going down here, which is equal to 1 plus beta over beta of IC1. Collector current, emitter current, remember, emitter current is tiny bit higher than the collector current. Also, there is a current in here, which is equal to 1 plus beta over beta times IC2. IC2 is final current, then we want to use it as a current source. There. Okay. And this is VBE1. VBE1, and then you have VBE2. So everything is in the handout. Don't need to write. So you start by applying analysis, DC analysis, that's all to it. You take that node, there are 3 currents. Current this way, current that way, the sum of the 2 bases, current going for the collector. So you establish IREF is equal to IC1 plus IB1 plus IB2. IC1 is equal to beta times IB1, beta times IB1, and IC2 is equal to beta times IB2. In other words, collector current of each transistor is a beta times of the base current of each transistor. Then I of the ref, IREF, is going to be equal to 1 plus beta over beta times IC1 plus IC2 over beta. So this becomes equation number 1. So we apply the KVL. KVL in this loop here. KVL. Going voltage, voltage, then reducing again voltage across that resistor. So it adds up to equation 2. This is the KVL. That is RE times 1 plus beta over beta IC1 plus VBE1 minus VBE2 minus RE times 1 plus beta over beta times IC2 equal to 0. That's just the KVL. It's this voltage plus that voltage minus of that voltage minus of this voltage. 4 terms over there. But then we know what is the relationship between IC1, IC2, and their base emitter voltages. This is the relationship. IC1 is IS, saturation current, e to the power VBE1 over VT. And IC2, IS, the same saturation because they're identical, e to the power VBE2 over VT. two identical transistors at the same temperature because they are fabricated on the same chip. Their VTs are the same, their VBs can be different. ISs are the same. IS, the saturation current. Dimension, the masking comes from the masking process. So, from 3 and 4, from these two last equation, if you substitute VBE equal to VT ln of IC1 over IS, okay, equation 3, marked equation 3, and VBE2 as VT ln of IC2 over IS, this is IS, equation 4. So if you make those substitutions in here, VBE1, you send it down here, VBE2, you send it down here, your final equation is going to look like this one. It's a big equation. RE 1 plus beta over beta, IC1 RE 1 plus beta over beta, IC2 plus VT ln of IC1 over IS minus VT ln of IC2 over VT, over VS, IS, excuse me, IS equal to 0. And finally, if you group them, you see there's a common factor in here. If you group, you will get RE times 1 plus beta over beta, IC1 minus IC2, finally is going to be equal to VT multiplied by the ln of here IC2 over IS minus ln of IC1 over IS. All the things closed. Now, the whole thing the truth will come out of here. You see, we have an IC1 minus IC2 product on this side. This is ln of A minus ln of B. Then it will be ln of A over B, right? The ratio. So this will be equal to VT ln of IC2 over IS divided by IC1 over IS. Okay, from top and bottom in here, interesting, the IS will cancel out, which is a very significant thing. The reason is our collector currents will be practically independent of the reverse saturation current in each transistor. Even if they change with temperature, and they do, ISs, they change with temperature, they cancel each other out. That's it, they knock out on both sides. So we get now the following here. Just let me write this, and then I'll answer it. VT ln of IC2 over IC1. That's IC1. Just focus on this part. That's all we needed, which in a minute we will discuss. What's your question?
What's ln? Is that like natural log or something?
Ln, natural log.
Oh, okay, got it.
Ln, natural log. So, here, this equation, which you see it's pretty complex, actually has a factor in it that can be replaced. Guess what? All of that equation on both sides can be replaced with the following identity. IC1 equal to IC2. Why? All right. There is one more difficult way of proving it, which, if I take this term here and I expand it with a Taylor series of the natural logarithm, we will see that this term and that term will exist on both sides of the equation, and it can be factored out and solved. But I'm not going to go there. Easier way. Substitute. If you satisfy that equation, both sides of the equation, then this statement is true. Check for truth. All right. If IC1 is equal to IC2, wouldn't that be 0? If IC1 is equal to IC2, wouldn't that ratio be 1? Lina 1 is 0. 0 is equal to 0. That's it. So we've got this conclusion here. That IC2 really, the collector current generated in here, is replica of the collector current in that transistor. Although we have two resistors in the emitter. That's what it proves. Although you have two resistors here, just like before, collector of current of here is copy of the collector current over there. But how are you going to relate the collector current here to IREF? That's easy, because if the collector currents are the same, betas are the same, then IBs are the same. So this will be equal to IC2 over a beta. So that total current will be twice of IC2 over beta. And we can relate to each other there. IC2 is equal to, it says, eliminate IC1 between 1 and equation 6. You finally come up with IC2 equal to beta over 2 plus beta multiplied by I ref. And it's the same as IC1. We got exactly the same equation as before. That we established the current in that resistor, in this resistor, and we got a current in here, which is almost duplicate of the current in the IREF, with a little short because of beta over 2 plus beta. There are current sources with an even better than that. You know, they are almost like exactly identical. But we won't go there. Now, what's the point of going through all that complication? I mean, if the two currents are the same, what's the point of that? You see? Because that one was the same thing, currents were identical. Okay, here is the point. It's the dynamic resistance, which is totally different. So in order to calculate the dynamic resistance, first of all, an example. There's an example here. So the analysis leads to that conclusion, and also utilizing all the equations that we derived, we can calculate IREF. So what is IREF in here? IREF, given that, which we needed for problem solving. So if you're bringing it to exam, bring that formula. Here, IC2 is equal to beta over 2 plus beta IREF, and IREF is equal to VCC minus VBE of 1, which is same as VB of 2, 1 plus beta, 2 plus beta, RE plus R ref. This is an important equation, number 9. And that is the one that we derived earlier, number 10. So given a circuit, you have no problem calculating the current in the second branch. Here is the example, 14K, you've got 500 ohm, 500 ohm, again XX, that means collector of that one is connected to, say, VCC, straight to the VCC. And we want to see what is IC2 eventually, coming through that branch between X and X. Okay? Using formula. Using formula means all of this analysis is condensed into that one. First, calculate IREF, how much is generated in that resistor, which we reduce the analysis to that one. So you substitute IREF 15 minus 0.7. VA is 80 volt, VB is 0.7 volt, VT is 25 millivolts, well, the beta is 100. So you substitute over there, equation 9, you find that IREF is equal to 0.986 milliamp. Then you calculate IC2 by that equation, bit number 10. This is from 9. We get that. Then from IC2, you will have beta over 2 plus beta times IREF is 100 over 102 times IREF is equal to 0.967 milliamp. Pretty close to that one, but little less. It should be a little bit less because of that numerator is smaller than the denominator. So we got those. Then VE2, VE of the 2, that is voltage in here, right there. How much is that emitter voltage? That is equal to I of E2 multiplied by RE. So that is equal to, instead of that, we will substitute 1 plus beta over beta IC of 2. Remember, that's a fast way of doing it. So you will have 1 plus beta over beta multiplied by IC of 2 times RE. So this turns to be 0.488 volt. That's the DC voltage established in here. 0.488 of a volt. 0.488 volt. I'm going for the VCE of that transistor. What's the collector to the emitter voltage? Remember, it's connected to the power supply, and that is a 15 volt. 15 volt, and XX is there, which I will make my final cuts between these 2 points. So this allows us to calculate VC of the 2. Here. VC of the 2 is 50. Therefore, VCE of 2, transistor number 2, is VC of 2 minus VE of 2, which is 15 minus 0.488, and therefore VCE of 2 is 14.51 of a volt, almost like 15 volt. And now the time is to determine what is RO. What is the dynamic resistance between collector and emitter of this transistor here? RO. So, classic formula for that one is coming from the Q point that you have in the plane. So ROs are always equal to VA, the VCE, divided by IC of transistor. That gives us the 1/, slope of those inclined lines. Here, RO adds up to be 80 volt for VA us 14.51 for the VCE. And you notice the 14 is pretty smaller than 80. Do you see that? So actually VCEs don't play that much of a role. They don't affect the value of RO. Divide by IC, yes, IC is important there. IC is 20.967 milliamp. Finally, RO ends up to be 97.7 kilo ohm. There it is. 97.7 kilo ohm is the dynamic resistance between collector to emitter. That's what we know. And GM, what's the GM of that transistor? This guy, okay. GM2 here. GM of 2, transistor number 2, is equal to IC2 divided by VT 0.986 milliamp over 25 millivolt, and that is a GM of 2, 39.44 millisiemens. Is that the GM of 2? Our pi of 2, our pi of that transistor, this guy, this part of the circuit, is equal to Vn over Gm2 is equal to 2.54 kilo. There. So we collected all the information that we need. These are DCs. These are just the DCs. What are we trying to analyze here? We are trying to analyze that. Given the DC circuit you have, everything DC, if I make a break here, I inject a small signal, between these 2 points, like 1 volt peak to peak maybe. So it will go above the power supply, 15, below the power supply, yes, we can do that. We want to see what kind of a current, plus minus, IT, test current will flow towards the collector. That's the whole objective. That will tell us, indeed, what will be the dynamic resistance of this current source. Otherwise, we know how much is the current. The current is IC2. Here. 0.96 milliamp, but it's going to change a little bit. There's something parallel with it. The resistance parallel with this one. So we want to know what is that resistance. In the case of a differential amplifier, that matters. You need to know the size of that resistance. There's no other way but analyzing the circuit. So that is the parameters we need. So we are equipped with our pi, GM, RO, 97 kilo ohm, which is pretty large, but see what will happen to it when we calculate the dynamic one. And now, the rest. Now we break here, we inject the test signal, and we want to know what is the test current, small signal test current that flows in there. There's got to be a current, because although it is a constant, but it is not constant because of the RO. RO is going to, as voltage goes up, the current will increase in that resistance. Therefore, it's not going to stay just a constant. It will fluctuate. But what will be the ratio? Is the output resistance the same as RO? Actually, no way. There would be no use if it was RO. It will be many, many times higher. So how do we do that? It comes from small signal analysis. So this is a large signal on those DC. And now watch the AC. small signal equivalent circuit across X test point. X test points. X is here, 1X is there. Okay, so you've got to go to the previous problem and start drawing the model. So this will be the model. Transistor on the left, this guy. We've got an RO for that transistor, collector to emitter resistance, which is almost the same as the RO for this side. Although you can argue, well, here, VCE is only 0.7 volt, but VCE is much larger. But don't forget what I said about that equation for ROs. ROs are VA plus VCE over ICs, right? VCE here is 0.7. VCE here is around 15 volt, right? 14 volt, it's big. But look at that. Whether you take that as 0.7 volt or you take it as 14 volt, VA being in the hundreds of volt, it's not going to make that much of a change on RO because both collector currents are nearly the same. So you can argue that ROs for both are the same. So here comes the model. Number one, supply is ground. This is the collector node of that transistor. Here. RREF, grounded. Take it to C1. Put RO, connect it to the E1, C1, and from here connect with RE to the ground. Put a current source in here. That current source is GM times VBE1. This is B of 1, and that is VBE of 1, VBE of the 1. Then we take this to B2, base of the second transistor. And indeed, this jumper here, this direct connection speaks of that link. Then you go to that side. You've got R pi. Then you have a VBE of 2. Then E of the 2, you have RE, and you've got the current source here. And then you have RO of the second transistor, which we calculated. And this is the C of the 2, which is this node here, C of the 2, the bottom X. This is where the X was, VT, IT, test current flowing in, and that current source is GM multiplied by VBE2, VBE of the 2. This is the VBE of the 2. Okay, RE. Now, about the dynamic resistance. You can argue that this is not like the previous case. You can argue. Why? Because if you're changing this voltage, you feel that something is going to change in this resistor because there's connectivity. So something is going to change in that resistor. The problem gets really complicated. If changes in there, it will go as, oh, we forgot the R pi for this guy. We forgot the R pi for this guy. So something is going to change in here, then it will reflect a change in this side. Well, the whole thing gets out of control, you know, it's too complex because there are too many sources involved in the whole thing. But there is a way of doing it. Generally, impedance looking in this direction here, between these 2 points, it is possible to show that impedance between these 2 points is 1 upon GM, which is a very, very low impedance. We can show that, you know. Simply, you've got to cut the circuit from here, calculate input impedance of this assembly, RF, RO, GM, R pi, and you will end up having impedance from X to X is approximately 1 over GM, approximately. 1 over GM. Those will not count. That R pi won't count. So it's approximately 1 over GM. The impedance from here to here is RE. So the total impedance viewed in that direction is going to be here, approximately 1 upon GM plus RE. That's total impedance viewed in that direction. However, this impedance is going to be also very small. Small in comparison to R pi. Because it is small, it's like a short circuit, we may assume that really the change of the current on that side doesn't reflect anything to this side because of such a low input impedance. On the other hand, impedance looking in that direction is awfully high. It is R pi plus 1 plus beta times this RE. So giant input impedance, very low output impedance to the left. So as if this impedance shorts that impedance from that terminal. Therefore, we will imagine that this is really connected to ground, 0 volt approximately, and this doesn't count. It doesn't count. It will simplify your analysis considerably. Then, what will be your equivalent circuit? Kind of a little modified equivalent circuit. It's this kind. So we need to prove VT over IT ratio has improved considerably. We need to prove that. Okay, so how do we prove that? Assume that IB2, the current that might exist here, is much, much smaller than the IT. That current. After all, see what that current is. Don't you think this IT is fair to say almost is equal to IE? Because that IT is collector current, see? Collector current, emitter currents are almost equal. Base current is much smaller than collector current, you see? Therefore, this current is going to be much, much smaller than the current existing in that resistor. Okay, again, I'll say that. This is IT, which is almost IC. ICs and IEs are almost equal because IBs are small. So I'm going to open up in here, like as if there is no current going in. This current, IB2, about equal to 0. Equal to 0. Write the node equation right in here, nodal equation. First of all, if IT is almost the same current as going here, IT approximately, we've got 1, 2, 3 branches in here. So these are the corresponding equations. GM VBE2, GM VBE2, which allows for that current, plus VT minus V of RE over RE, which is over RO, I'm sorry, RO, which is the current in that resistor, voltage here minus voltage here, and voltage here is IT times the RE, VRE, minus IT equal to 0. And that's the current going this way. Because this current goes away, those currents approach. That's why we have got those signs. Now, this quantity, V of RE, is already equal to RE times IT. So if you factor this whole thing out, and for the, if you factor them out, we are going to see, and V of RE and VBE2, okay? So you're going to get minus GM, minus GM. Let me just mention why we got that. GM times RE, IT, plus V of the T minus RE, I, T over RO minus IT equal to 0. Now, you may wonder how I jumped from here into here. Well, this is the VBE of 2. Look, plus, minus. This voltage is RE, IT. Take a critical voltage 1 in here. See what you will get. Go from here to here, RE, IT, negative to positive. Go from here to here, plus VBE2 equal to 0, because you come back to the same place. Therefore, VBE2 is equal to minus RE times IT. That is why I jumped from here straight into this equation. It came from there. It's a little hard to see, but you have to follow the voltages. So finally, this is our final equation, which is going to prove a formula which is almost universal. So you've got to remember that formula or bring it with your cheat sheets or whatever. And that formula is, if you get this ratio, IT, this will be the R dynamic resistance of current source. Parallel with IC2 equal to 1 plus GM, this is the GM of Q2, times RE multiplied by RO. Finished. You need this one. Whether you have a transistor or you get a MOSFET arrangement, it's the same formula. Except for the MOSFET, it will be even more accurate because you don't have that damn R pi. Here. This is the MOSFET version of the current source. RE, and that's the drain, source, that's the body. This is the body, which is always connected to the source, and that's the drain. VCC, and our ref, and this is the drain, and that's your X and X. That's it, gate, drain, source, again, gate, source, and the drain. This is exactly doing the same job as the BJT transistor is doing. Except there's one good thing about this guy, is when you're analyzing, you don't have this phase currents over there. It's much, much easier to analyze. By connecting the feedback, you'll be able to get the quiescent current, and the quiescent current will be duplicated on the other side. In the second transistor, second MOSFET transistor. Again, if you go through modeling, it will be similar to that one, except there won't be any RPi in here, which is sigh of relief. You know what? Because remember that I argued so much to dismiss this part of the circuit? There's automatically opening in here. So whatever is happening on this side is not going to transfer to the other side. Right? It's complete opening over there. So it will not excite the circuit on that side. Yeah. So we get exactly the same formula. 1 plus GM times RE. So when GM multiplies a resistance, it looks like a voltage gain. Do you see that? GM times RC, like a voltage gain. So you've got a voltage gain type of a product here, which is multiplying the RO. So we get multiples of RO for the dynamic resistance, not just the RO in the previous current source that we had. In the previous, both emitters were going to the ground. So this example is showing you. If you substitute the values that we have, GM is 500 ohm, GM is calculated before, 0.03944 Siemens, RE is 500 ohm, RO was 97.7 K. If you stick it into that formula, look what happens to the dynamic resistance, 2 mega ohm. So what was like 97 K for a current source, which is pretty high resistance, now it goes way higher to 2 mega ohm. Now, the next topic that I will analyze for you will be the differential amplifier. Without this concept, that differential amplifier, the modification we are getting on it wouldn't mean anything. So I had to go through the differences of the current source and a single resistor for the current source so you could understand the next topic. All right, so next time we come to class, straight away differential amplifier. And that will be your subject of midterm number 3. Differential amplifier, I'll explain it. Then you've got homework solutions. Homework solution number 4, is it number 6, I think? No, number 6. Homework solution number 6 is the reference point. There are plenty of amplifiers. I analyzed them. You'll go there and study.